Welcome to this problem-solving session. Today, we'll explore the LeetCode problem number 2073, time needed to buy tickets. This interesting problem challenges us to think critically about queues and efficiency. Let's dive into the details and break it down step by step. In this problem, we are tasked with calculating the total time it takes for a specific person in a line to finish buying their tickets. The scenario is described using a zero-indexed array called tickets. Each element in this array represents the number of tickets the corresponding person wants to purchase. The ticket counter operates in a round-robin fashion, where each person in the queue is served one ticket at a time in sequential order. Once the counter reaches the last person in the queue, it circles back to the first person and continues the process. If someone has already purchased all their tickets, they are skipped for the remainder of the rounds. The goal is to determine how many rounds it will take for the person at index k to complete their purchase. The input consists of the tickets array and the position k, and the output is the total time in rounds for the person at position k to finish buying all their tickets. Let's look at an example to understand this better. Suppose the input tickets array is 2, 3, 2, and the target index k is 2. This means there are 3 people in line, and the number of tickets each person wants to buy is 2, 3, and 2, respectively. During the first round, each person buys one ticket, reducing the array to 1, 2, 1. In the second round, each person who still has tickets buys another one, resulting in 0, 1, 0. At this point, the person at index k equals 2 has finished buying all their tickets. Counting the total number of tickets sold across all rounds, we find that it took 6 units of time for the person at index 2 to complete their purchase. Now, consider another example where the input tickets array is 5, 1, 1, 1, and k is 0. Here, the first person in line wants to buy 5 tickets, while the others each want just one ticket. In the first round, the first person buys one ticket, reducing their count to 4, while the others each buy their only ticket, leaving 4, 0, 0, 0. In the subsequent rounds, the first person continues buying one ticket per round until their count reaches 0. This process takes a total of 5 rounds for the person at index 0 to finish purchasing all their tickets. Thus, the output for this example is 5 units of time. Finally, let's review the constraints and edge cases. The length of the tickets array, denoted as n, satisfies 1 equals n equals 100. Each element in the array, representing the number of tickets a person wants, lies between 1 and 100. The target index k is guaranteed to be within the bounds of the array, specifically 0 equals k less than n. For edge cases, consider a scenario with only one person in the queue. For example, if tickets equals 5 and k equals 0, the total time is simply the value of tickets, 0, as there is no one else to share the counter. Another edge case is when all individuals want just one ticket. Here, the total time is equal to k plus 1 because each person finishes their purchase in exactly one round. Lastly, if the tickets array contains large values, such as 100, 100, 100, with k equals 1, the solution must handle this efficiently without excessive computation. These constraints and edge cases ensure that the algorithm is robust and performs well under various conditions. The problem we're solving involves a ticket counter where people are served in a round-robin manner. Each person in the queue has a specific number of tickets they want to buy, as given in the tickets array. The challenge is to determine how much time it will take for the kth person in the queue to purchase all their tickets. A few key observations simplify this process. First, the round-robin behavior means the counter serves one ticket per person, cycling back to the start of the array after reaching the end. Second, each ticket purchase reduces the ticket count for that person by 1. Third, as soon as the kth person finishes buying all their tickets, the process stops, regardless of whether others still need tickets. Lastly, the time contribution of each person depends on the smaller value between tickets, I, and tickets, k, since individuals can only be served for as long as the kth person remains in the queue. These observations lay the foundation for solving the problem efficiently. One approach to solving this problem is the brute force method, where we simulate the ticket buying process step by step. The intuition here is straightforward. We iterate through the queue in a cyclic manner, decrementing the ticket count for each person who still needs tickets. Using a while loop, we repeat this process until the kth person's ticket count reaches 0, keeping track of the total number of iterations along the way. This approach ensures we capture every step of the process as it unfolds. However, the main drawback lies in its inefficiency. The time complexity is max_tickets, where max_tickets is the highest value in the array, because we might traverse the array multiple times depending on the ticket counts. While the space complexity is low at 1, the repeated iterations make this approach impractical for large inputs or scenarios where tickets, k, or max_tickets is very high. An optimized approach offers a more efficient solution by calculating the total time directly instead of simulating every step. The key idea is to determine the contribution of each person to the total time. For individuals at positions less than or equal to k, their contribution is simply their ticket count, since they will be served until they run out of tickets. For individuals at positions greater than k, their contribution is limited to the smaller value of their ticket count or tickets, k, because the process ends as soon as the kth person finishes buying their tickets. To implement this, we initialize a variable time to 0 and iterate through the array. For each person, we add either their full ticket count or the constrained value, depending on their position relative to k. At the end of the iteration, the accumulated time gives the total time required. This eliminates unnecessary steps and ensures we arrive at the result efficiently. The optimized solution is highly efficient, with a time complexity of n, since we only traverse the array once, and a space complexity of 1, as no additional data structures are used. This makes it significantly faster than the brute force method, especially for large inputs. The advantages of this approach include its scalability and the elimination of redundant computations, making it well suited for competitive programming scenarios. Comparing the two strategies, the brute force method is easier to implement and understand but becomes computationally expensive as input size grows. The optimized approach, while requiring a deeper understanding of the problem, strikes a balance between clarity and efficiency. Given the constraints of LeetCode problems, the optimized solution is the clear choice, providing both precision and speed without compromising on simplicity. The problem asks us to calculate the total time required for a specific person, denoted by index k, to purchase all their tickets at a ticket counter that operates in a round-robin fashion. Each ticket is served one at a time, and the counter processes people sequentially in a cyclic order. If a person still has tickets remaining, they are served one ticket, and the process continues until the kth person has no tickets left. To solve this, we first need to understand that only the tickets of people in the queue before the kth person affect how long it takes for the kth person to finish. For each person, the number of tickets they contribute to the total time is limited by the number of times they are visited in this round-robin sequence. These observations form the foundation of our approach to solving the problem efficiently. To design the algorithm, we start by initializing a variable, time, to 0. This will track the total time required. We then iterate through the tickets array, processing each person individually. For people before the kth index, their contribution to the total time is the minimum of their ticket count and the number of rounds the kth person goes through. For the kth person themselves, we add all of their tickets because they need to finish them completely. For people after the kth index, we only count their tickets up to the point where the kth person finishes, which is why we take the minimum of their ticket count and one fewer than the kth person's tickets. At the end of this process, the accumulated time gives the result, which is returned. The use of the min function is crucial because it prevents us from overcounting tickets for people who no longer contribute to the total after the kth person has finished. For instance, if someone has more tickets than the kth person, their contribution is capped by the rounds the kth person participates in. Edge cases include scenarios like when there is only one person in the queue, where the total time is simply the tickets required by that person. Another case is when all people before the kth person have fewer tickets, meaning their contributions are limited and do not delay the kth person. Even for very large values of tickets, k, the algorithm remains efficient because it avoids unnecessary calculations by directly limiting contributions mathematically. The solution relies on iterating over the array and a single time counter, making it simple and effective. The algorithm is highly efficient, with a time complexity of n, as we make a single pass through the array and perform constant time operations for each element. The space complexity is 1, because we do not use any additional data structures beyond the input array and the time counter. Let's go through an example to see how this works. For the input tickets equals 2, 3, 2, and k equals 2, we calculate the contributions. Person 0 contributes min, 2, 2, equals 2, person 1 also contributes min, 3, 2, equals 2, and person 2, being the KTH person, contributes all of their tickets, which is 2. Adding these gives a total time of 6. For an edge case like tickets equals 5 and k equals 0, there is only one person, so the total time is simply 5, matching their ticket count. These examples illustrate the correctness of the algorithm for both typical and edge cases. The algorithm can be further optimized by entirely avoiding the simulation of the round-robin process. Instead of iterating through the queue repeatedly, we calculate each person's contribution directly using mathematical operations. This eliminates unnecessary iterations and ensures the solution is as efficient as possible. Additionally, we can implement an early exit condition. If we've processed up to the KTH person and their tickets are fully served, there is no need to compute further contributions. These optimizations maintain the simplicity of the approach while improving its performance, ensuring it handles both small and large inputs effectively. This Python implementation solves LeetCode problem number 2073, time needed to buy tickets. The goal is to calculate the total time required for the KTH person to buy their tickets in a round-robin manner. The function time required to buy takes two inputs, tickets, a list where tickets, I, represents the number of tickets person I needs, and k, the index of the person whose total time we are calculating. The variable total_time is initialized to 0 since we need to accumulate the total time as we iterate through the list. We then loop through each person in the tickets list using a for loop. For each person, we determine how many tickets they will buy before the KTH person finishes. If the current person's index I is less than or equal to k, they are involved in the round-robin process during the KTH person's turn, so we add the lesser of their total tickets or the tickets required by the KTH person. If the index I is greater than k, they only contribute to the process until the KTH person finishes, so we add the lesser of their tickets or tickets, k1. Finally, after summing these contributions, we return total_time, which represents the time required for the KTH person to buy their tickets. This solution is efficient and leverages the sequential nature of the problem to calculate the time in a single pass through the list. This is the Java implementation of LeetCode problem number 2073, time needed to buy tickets. The logic mirrors the provided Python implementation, with adjustments for Java syntax and conventions. Key differences include explicit type declarations, the use of Java's math.min method, and the structured class definition. The function calculates the total time required for all customers to buy their tickets, considering the constraints given in the problem. Let's start with example 1, where the inputs are tickets equals 2, 3, 2, and k equals 2. First, we initialize total_time to 0, which will keep track of the total time required for all the people in the queue. Now, we begin iterating through each person in the queue. For I equals 0, the first person needs 2 tickets. Since their position I is less than or equal to k, they can buy up to min, tickets, 0, tickets, k, which is min, 2, 2, equals 2. We add this to total_time, making it 2 so far. Next, for I equals 1, the second person needs 3 tickets. Again, since I is less than or equal to k, they can buy up to min, tickets, 1, tickets, k, which is min, 3, 2, equals 2. Adding this to total_time gives us 4. Finally, for I equals 2, the third person, who is also the target person k, needs 2 tickets. Since I is still less than or equal to k, we add min, tickets, 2, tickets, k, equals min, 2, 2, equals 2 to total_time, resulting in a total of 6. So, the total time required for everyone in this example is 6. Moving to example 2, the inputs are tickets equals 5, 1, 1, 1, and k equals 0. Again, we start by initializing total_time to 0. For I equals 0, the first person, who is also the target person k, needs 5 tickets. Since I is less than or equal to k, we add min, tickets, 0, tickets, k, equals min, 5, 5, equals 5 to total_time, making it 5 so far. For I equals 1, the second person needs only 1 ticket. However, since their position I is greater than k, they can only buy up to tickets k1, which is min, tickets 1, tickets k1 equals min 1, for equals 1. Adding this to total underscore time gives us 6. Similarly, for I equals 2 and I equals 3, both need 1 ticket, and they are also after k, so they each contribute min 1, for equals 1 to total underscore time. Adding these sequentially results in a total of 8. The total time required for example 2 is therefore 8. Now, in example 3, we consider a simpler case with only one person in the queue, where tickets equals 4 and k equals 0. We initialize total underscore time to 0 as always, and since there is only one person, we only need to process I equals 0. This person needs 4 tickets, and since their position I is equal to k, they can buy up to min, tickets, 0, tickets, k, equals min, 4 equals 4. Adding this to total underscore time, we get a total time of 4. Finally, let's summarize how the algorithm works. The key idea is to iterate through each person in the queue and determine how many tickets they can buy before the target person k finishes. For anyone at or before position k, they can buy up to tickets, k tickets, while those after k can only buy up to tickets, k1 since k will leave the queue first. The min function ensures that we never exceed the number of tickets a person actually needs, ensuring the calculation is both accurate and efficient. This systematic approach ensures we calculate the total time correctly for any scenario. To determine the time complexity of our solution, we begin by analyzing the key operations. First, let's define n as the length of the tickets array. The solution contains a single for loop that iterates over the array exactly once. This means the base contribution to the time complexity is O(n). Now, within each iteration of the loop, there are a few operations to consider. The condition if I equals k is a simple comparison, which is a constant time operation, or O(1). Similarly, the calculations min, tickets, I, tickets, k, and min, tickets, I, tickets, k1, are also constant time operations. Since all of these operations inside the loop take O(1) time and the loop runs n times, the total time complexity of the solution is O(n). This holds true for the best, average, and worst cases because the loop always processes the entire array, regardless of the input values or the position of k. Now, let's evaluate the space complexity of the algorithm. The solution uses a single integer variable, total underscore time, to accumulate the total seconds required. This variable occupies a constant amount of space, or O(1). Beyond this, no additional data structures are created, and the amount of memory used does not depend on the size of the tickets array. This makes the overall space complexity O(1). To put this in perspective, consider a naive or brute force approach. Such an approach might involve explicitly simulating the ticket buying process by decrementing ticket counts one by one and iterating through the array repeatedly. This would result in a time complexity of O(n** max tickets, ***, where max tickets is the highest number of tickets held by any person. Our solution avoids this inefficiency by calculating the total time in a single pass, reducing the time complexity to O(n), and maintaining the optimal space complexity of O(1). Finally, let's solidify our understanding with a mathematical proof of the big O notation. The size of the tickets array, denoted as n, dictates the number of iterations performed by the algorithm. Each iteration involves only constant time operations, such as comparisons and min calculations. As a result, the total time required is directly proportional to n, confirming the time complexity is O(n). On the other hand, the space complexity is independent of n. The algorithm does not allocate any additional memory based on the input size, using only a single variable for computation. This ensures the space complexity remains O(1). To summarize, the time complexity is O(n), the space complexity is O(1), and this efficiency holds across the best, average, and worst cases. Compared to a brute force simulation, which would involve a time complexity of O(n** max tickets, ***, this solution is significantly more optimal. When solving this problem, there are some common mistakes to watch out for. First, not accounting for the round-robin order is a frequent issue. It's tempting to think that once you've calculated the tickets for a person, you can completely skip over them. However, the round-robin process means each person is served in cycles until their tickets are fully bought. Skipping someone prematurely would result in missing cycles and incorrect results. Another common mistake is incorrectly handling the stop condition. Once the target person, or the KTH person, has purchased all their tickets, the process should terminate. If you continue simulating the process beyond this point, you're introducing unnecessary computations, which could lead to incorrect time calculations. Lastly, overcomplicating the solution is something to avoid. Some people simulate every single step in the process, but this isn't always necessary. By recognizing patterns or using mathematical shortcuts, you can simplify the problem and achieve a more efficient solution, especially when working with larger inputs. Another area where mistakes often occur is with indexing errors. Since arrays in programming are typically zero-indexed, confusing this with one-indexed systems can lead to off-by-one errors. For example, miscalculating the target person's position in the array could result in incorrect results or runtime errors. Additionally, ignoring edge cases can cause major issues. For instance, what if all the values in the tickets array are 1? Or what if the KTH person has 0 tickets, assuming the problem constraints allow this? Overlooking these scenarios can result in incorrect outputs or even crashes. Addressing these edge cases in your solution ensures that it's robust and accounts for a wider range of inputs. Now let's focus on some insights that can help you tackle this problem more effectively, especially in interviews. One key pattern here is recognizing that while the problem appears to involve simulating a queue, it can be optimized. The wait time for the KTH person depends on two things: the tickets required for those ahead of them and the remaining tickets for people who are served after them but before their turn ends. An important optimization opportunity lies in avoiding a step-by-step simulation. Instead, calculate the total time using a mathematical approach. For each person in the array, you can take the minimum of their ticket count and the tickets required by the KTH person to determine their contribution to the total time. This reduces the complexity from a brute force O, n asterisk max, tickets, to an optimized O, n. While brute force might work for small inputs, this optimized approach is far more efficient for larger arrays. Remember, understanding these trade-offs is critical for writing scalable solutions. Finally, let's talk about some additional considerations and related problems. Be ready to explain edge cases, such as scenarios where everyone in the array needs the same number of tickets or when the KTH person is the very last in line. These examples can help demonstrate that your solution is well-tested and robust. For related problems, LeetCode 621, Task Scheduler, involves scheduling tasks with constraints like cooling intervals, which has similarities to round-robin constraints. Another one is LeetCode 1700, Number of Students Unable to Eat Lunch, a simulation problem where serving students follows a specific order. LeetCode 1823, Find the Winner of the Circular Game, involves cyclic traversal, which mirrors the round-robin concept discussed here. Lastly, LeetCode 225, Implement Stack Using Queues, isn't directly related but provides great practice for queue-based logic and simulation techniques. Exploring these problems can deepen your understanding and help you recognize patterns in queue-based simulations. Great job! To wrap up, we've learned how to simulate a queue efficiently and tackled a real-world inspired problem. Remember the importance of analyzing edge cases and refining your approach for better performance. If you enjoyed this, please like, subscribe, and stay tuned for more coding tips and solutions. Until next time, happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!